to address what I left off the last video with, which is this idea of what you might call the nearest point error. I don't know if this has an actual name, because I honestly have never taken a statistics class. So, I'm really just flying by the seat of my pants here. And, the last couple videos and this video are really just me asking questions and trying to answer them. I don't actually know what the right answers are supposed to be, which is really what, math and science in general is all about. But anyway, if any of you who have taken a stat course, know that this is supposed to have some kind of fancy name, let me know. I'm just going to call it the nearest point error for the sake of this video. So, one other brief thing that I wanted to address before I move on to this. In the last video, I forgot to mention how we know that value of m and that value of b that we got, how we actually know that corresponds to a minimum. Which, of course, you wouldn't want to accidentally maximize the error if you're supposed to be minimizing it. You want to make sure that you actually have a minimum. So, the way that you know it's actually supposed to be the minimum and not the maximum, is that we were optimizing this error function. Sorry, not sigma, e. We're optimizing this error function, which looked like a sum of quadratics, right? yi minus mxi plus b squared, right? So we were trying to minimize this thing, and the thing that I wanted you to notice, but I didn't make explicit, so I just wanted to take a second to do so, which is that all of these are necessarily bigger than or equal to 0. And adding them up, of course, that's going to preserve the fact that all of this is still bigger than or equal to 0. And so we've got this function that's always bigger than or equal to 0. And in particular, this function will have no maximum. All right. What that means is that you can always change the values of m and b that will make you get arbitrarily far away from your data set, in which case you'll have arbitrarily large error. Right? I mean, just imagine sending b, the y-intercept of your line that you're working with, take b to be some number that's going to infinity, that line of best fit is just going to keep getting farther and farther and farther away from your data set, which is a fixed set of numbers. All right, so this thing's not going to have a maximum. And because it's always bigger than or equal to 0, if it does have a critical point, it's going to at least be a local minimum, if not a global minimum. And so it's not too hard to check that the critical point that we found in the last video, these really wacky values for m and for b, these have to correspond to a minimum. All right, there's no other way around it because this function's always positive and it has no maximum. All right, so it's gotta correspond to a minimum. So, what I want to do now is to address this possibly much harder question of how we actually minimize the error if we're not just using the vertical variation error like we were in the last video, right? So we've got our data set. I'll just draw a few dots here. There's our data set. These are xi's and yi's. And the idea is that we can find some line of best fit, maybe it's right there, which will, sort of minimize some kind of error that's going on here. In the last video, we looked at the errors that looked like this, the vertical variation errors. And the reason why this was nice was that we knew what x values we were working with in every one of those, these little individual error calculations. we knew that they were always going to have the same x value. The only thing that was changing was the y value. And so that was was enough to make it so that we could actually do a nice calculation for this. What I want to do now is try to fine-tune that a little bit, at least look into what it would look like if we tried to fine-tune it a little bit. And by fine-tune it, I mean instead of looking at the vertical variation, which you'll notice the vertical variation, because we're only talking about right triangles here, right? If you turn the video, sort of at like a 45-ish degree angle, you'll see that really we're just talking about right triangles here. And so, you've got this leg of the right triangle, which is what we worked with in the last video. And what I want to do is, that would be the hypotenuse, I guess. You would want to look at the perpendicular, right, the height of that triangle. So this green thing I just drew, this little green segment, right, and we can draw them for all of them. Little green segments that we can draw. These are nice because these are the shortest distances between our data set, which are the dark blue dots, and the red line. Right? These are the shortest distances. So you can ask the question, if we minimize these shortest distances, then in some sense we'll be getting the line that is, quote-unquote, closest to our data set. Whereas when we minimize these blue hypotenuses, I don't know what the right way to pluralize that is. I guess it's hypotenuses. In minimizing these blue hypotenuses, are we actually getting the line that's closest to the data set in some sense? Okay, so what I want to do now is look at the these shortest distances, right? These green distances, which are the shortest distance from the data set to the red lines. And I mentioned in the last video that each one of these, we've seen pictures that look like this before. So that's the first thing that I want to address. All right, we have seen something like this before. In fact, it's kind of a fundamental part of this class. So our line is going to be given by y equals mx plus b. And what I want us to recognize is a couple things. Okay, so we have seen many pictures that look just like this. However, not exactly in this context. Right? We have to tweak what we're looking at a little bit to make it exactly like what we've seen before in class. So let me just, remove all the suspense for you here. I know it's killing you. What we've seen before in class are a lot of pictures that look like this. Right? We have some vector, call it v, and we have some other vector, call it u. And what color was I using? Green? Yeah, so this green shortest distance would be like that. And what are we looking at here, right? What are these things? Let me use red to denote this. That vector right there, we know and love. This is our projection onto V of u, our orthogonal projection of u onto V. And that means that this green thing here, right, we have seen this green thing before. Should point down, I guess. This, is that right? No, it points up. Right, tip to tail. So if I put green thing at the tip of the red one, then it should result in giving me u back. So it should point up. That's a very minor point. The important thing is that we know what this is. This was what one of the questions on homework 1 was all about. That is the fact that u can be reconstructed via what I was calling u perp plus u parallel. Alright, so this is the part of u that is orthogonal to v. That's what this is. And let me use the colors that I just established to reconstruct this, right? So u is given by this dark blue color. U perp is what is in green in my diagram, and U parallel is what's given in red. Right? This is really the projection down here, the projection of U onto V. Okay? So we saw exactly how to calculate this. This green vector, therefore, is equal to U minus U parallel. In other words, this is U minus the projection onto V of U. And we know exactly what the projection onto V of U is. We know exactly what the formula is. This is U dot V over V dot V, if you like, in the direction of V. All right, so we know exactly how to do this. And then U minus that is equal to U perp. And what we're saying in this picture, right, let me just move back up here. What we're saying in this picture is that the length of any one of these straight lines between our data set and the red line, well, that's really the length of one of these perpendicular vectors. So if we have a formula for how to calculate these perpendicular vectors, which we do, it's right here, then we know how to calculate the length of that vector, right? We just take the length of this thing and we'll be good to go. Okay, so digest that, right? Pause the video at this stage. Make sure this makes sense, right? How this picture up here and this picture down here are correlated. All right, make sure you have a firm grasp on that. Pause the video if you need to rehash everything. Make sure you can draw this diagram on your own, and really have this concretely in your head. And then resume, and we will move on to the next thing, which is to recognize that this picture up here, this line picture, this is not exactly the same as this vector picture that I drew here. Right? They are a little bit different. And to see how they're a little bit different, you've got to think about what the line picture, right, up here, is actually saying in terms of vectors. Not in terms of lines, but in terms of vectors. Okay, so let's draw in some of these, some of the vectors of things that we might be looking at. All right, so let's just look at this first data point. Okay, this first data point, not a great picture. That's a little better. All right, this would be the first data point as a vector. Right, this would be x1, y1 as a vector. It would be that arrow from the origin up to that dot. However, the corresponding point, right, let me illustrate it in green here. Right, that green dot is the point on our line of best fit, which is closest to our data vector, x1, y1. And now if I draw that vector in red, remember, vectors are going to start from the origin. There is the vector that extends out to our line of best fit at the point that's closest to our data vector. And yeah, I mean, hopefully you can see that this is not exactly what we want to consider, right? At least not in the same way that I drew it down here just a second ago. All right, so, we have to be a little bit careful, I think is the point that I'm trying to make, right? We have to be a little bit careful about how we do this. So, yeah, I mean, take a minute and pause this video and think about how you can address the issue that's going on here, right? Number one, why is this an issue? And number two, how can you address this issue, right? What am I actually saying is a problem here? Is there even a problem here, right? I mean, if you don't see a problem with this, then have a firm understanding of why you don't see a problem with this, you know? So just try to wrap your head around what's going on here, right? The issue that I'm claiming is present is that in the line picture, our vectors, right, when we vectorize everything, vectors will extend out from the origin because we've given them coordinates, and so they should have their base points rooted at the origin. All right, so try to wrap your head around what's going on here, and then when you do that and you feel either comfortable or super uncomfortable with what's happening, resume the video. Okay, so the point that I'm trying to make here is the following. If we look at our line picture, everything is very predictable in a sense because everything is supposed to be at right angles. Sorry, those are supposed to be little right angle markers. Everything's supposed to be at right angles to the line, right? All of these little green things are at right angles to the line. And, you know, in this picture, the green thing's at right angles to whatever that thing down there is, right? Which is why I drew that vector on the bottom in red. This is supposed to be a direct, you know, illustration of what's going on in the line picture, which is red in the line picture, right? So everything's supposed to be, the green arrows are supposed to be orthogonal to the line. However, if we look at you know, the relationship between different data points and the vector versions of the line, well, we'll start to see a problem. Let me use a different data point here. Let's use maybe the second one. All right, so let me clean this up a little bit. All right, let's get rid of that. Just forget that data point was ever there. Let's look instead at the second one. Right, so there's the vector, the data vector that's coming out of the origin, and there is the line vector that extends to this nearest point, which is that green dot on the line to that data point. And if I draw this picture, you know, outside of the context, so I'm going to take this and blow it up a little bit. If I take it outside of the context of this line, which is on there, and I just draw everything relative to the origin, then I end up with something that looks like this, and I've got this green line that connects these two things together. All right, and hopefully you can tell from the picture here that neither of these angles is a right angle, right? It's impossible for this to be a right angle because if you look at the original picture, the green thing is orthogonal to the line. It can't be orthogonal to either one of those two vectors because neither of those vectors is parallel to the line. Okay, so this is not, right, the three angles there, none of those three angles are right, are 90 degrees, or pi over 2. So we're not dealing with a right triangle here. All right? This is a problem, right? We know that green line, this green line connecting the data set to our line of best fit, it's got to be perpendicular to the line of best fit. Otherwise, it won't be the shortest distance. So, right, in other words, it's not going to look like this picture, right? These two pictures are incompatible. They're not the same thing. And that is an issue. Right? It's an issue we need to address. So, what we are going to do, and hang on, let's think for a second about why this is happening. Right? Why is this problem occurring? And the real reason why this problem is occurring is because our line doesn't go through the origin. This is really why the problem is occurring. We are trying to project vectors, which are rooted in the origin, onto a geometric object, which itself is not rooted to the origin. And, we talked about how we can, move vectors around, sort of free-floating, and redirect them, not redirect them, but reposition them so that their base point is anywhere in space, as long as their direction and magnitude are the same. And that's true. But once you start comparing geometric objects like lines that don't go through the origin to vectors, well, all of those things have to be talked about in the context of an origin, because the line is rooted in this xy plane according to what that value of b is. Right? So the origin matters a lot for this line. Whereas, the origin doesn't matter so much for vectors. So what we're saying here is that in order for the line to be described by vectors, well, they've got to be described by vectors that are rooted to the origin, because our line is rooted to this place on the y-axis. 0, b, whatever b is. And so the vectors that describe this line come out of the origin, and they aren't parallel to the line itself. Right, so this is just a wacky problem that we have not really encountered before. I mean, we've encountered it in the context of space curves, but we didn't really have to make a big deal out of it. But we do now. Right, so the question is, how do we fix this problem? So here is a similar picture. All right, you can see that we've got a different data set, and we've got a line of best fit, or a line anyway. It's not necessarily the right line, but it's a line. And our data vector is in dark blue. Our line vector, which describes this point, which is closest to the data point that lies on our line, and this red vector is the one that extends out to it. All right, and this triangle here is not a right triangle, which is a problem. So, what we are going to do to fix this issue is the following. Let me use a different color here, maybe brown. What we're going to do is we are going to shift everything in space around the needs of this line. All right, so basically this line needs to go through this point 0b on the y-axis. And so what we're going to do is just sort of move everything in space around that requirement. And what this is going to amount to is just shifting everything. So what we're going to do is we are going to shift the entirety of space in this picture up a little bit. Right? So now our line will go through the origin, and what we have to do is adjust these other vectors accordingly. All right, so the point of this is that now this brown vector here is the vector that describes that green line, that green dot that is closest to our data point, that lies on the line. And this blue vector is now the one that's a little bit wonky, right? This is the one that's now not rooted at the new origin, which now is on the brown axes. Right? So this blue vector is no longer rooted at our new origin. So what we have to do instead is just shift that vector, basically, right? We shifted the line to make the line go through the origin, and we're just going to shift that vector accordingly. Okay? So the idea here is the following. We are going to have a new data set and a new line. And our new data, well, our new line, that's the easy part. So our new line is going to be the old line, which looked like x mx plus b. And we're just going to shift the entirety of space around it and get rid of that y-intercept. All right, so this is going to end up being x mx. Right? And notice that when x is 0, this gives you 0, 0. In other words, this thing goes through the origin. All right? That's how I knew to subtract 0b instead of adding it, for instance. So this is the same thing as saying, it's x times 1m. And this 1m thing, we're going to denote that by L, right, the lowercase l vector. This is the direction of our line. And that's the direction of the line as a vector. And this subtraction of 0b thing, this is what's going to generate our new data set for us. All right, so our new data set, it used to look like as vectors xi, yi. Right, this is the old data set. The new data set, we're just going to shift everything accordingly. Let's just subtract 0b from that. And this will be our new data set. All right, so we're going to have our new data is going to look like xi in the x component, yi minus b in the y component. And our new line is going to look like x times this L vector, which is the direction of our line. Okay, so this is going to root everything in a new origin for us, right? Everything will be rooted in the origin that is brown in this picture. And that's going to be great for us, right? This is going to give us a picture that looks something like this. Let me draw a new one. Right, so in the brown axes, which is just the shifted axes, our line now moves through the origin, and our new data vectors are going to connect to the old data points, right? The points are still the same relative to one another. They're going to connect to those data points, and we're going to get those little lines right there. And so everything, the little green lines, that is, which are the nearest points, the lengths of the nearest points from our data to the line of best fit. Right? In other words, this is a picture that's entirely rooted in the same origin. Everything's relative to the same origin now, just by shifting everything. And these pictures now are all 100% coherent with everything that we had on the last page, which is right here. Right? All of this stuff now makes sense. Okay, so that's why we need to shift everything in space, so that this picture is the same as this picture that we know, and well, maybe we don't love it, but we at least know it, and that's important. Okay, so in the next video, I'm going to talk about how we use this new data set and new line to go ahead and answer the fundamental question at the heart of this, which is, how do we actually calculate these shortest distances, and then eventually, how do we minimize them?